Welcome you all in the 12th lecture of Electronics Measurement and Instrumentation. It is part 2 of the CRO cathode ray oscilloscope. In this lecture, I will discuss measurement of different electrical quantities with the cathode ray oscilloscope. So, this is the outline of my lecture. First of all, I will discuss the measurement of DC voltage, then the measurement of AC voltage. In AC voltage, I will discuss the measurement of amplitude and frequency, then the measurement of phase shift between two signals, and then how do we test a component and what are the different precautions required during the measurement of CRO. So, first of all, as we know that any electrical quantity, that is any voltage, has following components. One is the amplitude and second is frequency and third is phase shift. So, these are the three part of any electrical signal. So, any electrical signal is represented by y is equal to a sin omega t plus phi, where omega t is the time period of the signal and omega is the frequency of the signal. Omega is equal to 2 pi t, where t is the time period, f 2 pi f, where f is the frequency and 1 by f is the time period, and phi is the phase angle of the signal. So, by measuring any signal, we can measure from CRO. One is peak to peak amplitude from minimum to maximum value. We can measure the amplitude, means one side of the signal, that is from 0 to positive highest value or 0 to negative highest value, and then we can measure the time period of the signal, and by measuring the time period we can find out the frequency of the signal. So, for that measurement, as I have discussed in last lecture also, we have two control knobs with us. One is the voltage per division, another is the time per division. So, by changing the position of volt per division and time per division, by changing the position of volt per division, we can either increase the height of the signal or decrease the height of the signal. That depends upon the position of the volt per division. Here basically we are varying the voltage at the whatever applied at the vertical deflection plate. Similarly, by changing the this time based signal, that is the millisecond per division, or this second knob, that is the time per division, we can change the position, we can expand the signal in the x direction or we can compress the signal in the x direction. So, as we know in the CRT that we will discuss in next lecture, in CRT we know that there are two pair of plates. One is one pair of plate that is known as the vertical deflection plate, and other pair of plate which is known as the horizontal deflection plate. So, the vertical deflection plates which controls the movement of electron in the vertical direction, but they are placed horizontally, they are placed like this way, and they controls the movement of electron in the vertical direction. That means this movement of electron is proportional to the unknown amplitude, and when we apply a signal to the input of the CRO, so that will change the signal at the vertical plates which are placed horizontally. So, the voltage at these two plates, the voltage varies between these two plates, and because of that variation the signal will move in the vertical direction. Similarly, there are two parallel plates which is situated in the CRT, and they are placed horizontally, and they control they are placed vertically in the CRT, but they controls the movement of electron in the horizontal direction. So, they are placed like this way and they controls the movement of electron in the x direction. So, basically they controls the time based signal. So, this type of suppose the first thing what I have shown here, that when we have not applied any signal at the horizontal deflection plates, then what will happen, there is no movement of electron beam in the horizontal direction. So, when we apply a signal at any of the input of the CRO, then that input is applied to the vertical deflection plate, and because of that input the electron move from up down, from up to down and down to up. So, you will see electron movement at this vertical position, but there is no movement in the horizontal position. So, it will show the peak to peak value of the signal, but it will not show the time of the signal or the frequency of the signal. Similarly, if we put a signal at the horizontal plate, but no signal at the vertical deflection plate. So, what will happen? There is no vertical movement of the electron beam, only the electron spot will move in the horizontal direction. So, you will get a horizontal trace, but not a vertical trace. Suppose we apply both the signal, same sinusoidal waveform at horizontal and deflection plate both, then we will get this type of pattern, a diagonal line. So, it means when we want to see the behavior of the signal, we want to see the waveform of the signal, then we have to apply the signal at the y plate, y deflection system, that is the vertical deflection system, and we will apply a time based signal at the horizontal plate. So, suppose first of all we want to measure DC voltage. So, as we know DC voltage has no repetitive value, means it is a straight line. If we see the DC voltage is like this way, this is suppose the axis. So, this is the DC voltage and this is the amplitude of the signal. So, suppose we want to measure only the amplitude of the signal, we do not want to see the signal behavior. So, simply we will switch off the time based signal, means we will not apply any input to the horizontal deflection plate. So, switch off the time based signal, then you will see a spot movement from here to suppose the spot is here. So, it means this position, this y is showing the amplitude of the signal. So, the spot will move only in the one direction, and suppose if we by adjusting the x position of the signal, we can place that spot at the midpoint of the screen. So, we can see the amplitude of the signal. So, when we want only to measure the amplitude of the signal, then we have to switch off the time based generator. So, time based generator is turned off, and then suppose this y, which is having y, this knob, the previously I discussed the knob of volt per division, suppose it is at 2 volt per division, and this amplitude is suppose 1.5 division, 1 division whole and 0.5 of the 1 division, that means 1.5. So, the total amplitude will be 1.5, that is the division covered by this spot, into 2, that is the 2 volt per division. So, the amplitude is of 3 volt. Similarly, suppose we want to see the waveform also. So, at that time what we will do? We will put this, we will vary this knob, that is the volt per division knob of that particular channel where we have applied the input signal. So, by varying this knob, we can change the position of the amplitude of the signal position. So, suppose if the amplitude of signal is very high and it is not appearing inside the screen, then we will change this position so that it can come inside the screen and so that we can measure the signal. So, when we want to measure DC signal, then as I have discussed in previous section, this knob should be at DC position. If we want to measure AC signal, then this knob should be at AC position. So, similarly, we will put our input at this position. This is showing your one of the probe. So, probe is put at this position, and by varying the value of millivolt per division or the volt per division, we can see we can measure the amplitude of the signal. Suppose if a small variation between, suppose there is 10 millivolt, then there is 20 millivolt. Suppose we want a signal in between that, then we will vary this knob of the level, this knob which is inside the time per division. So, in this way we can measure the waveform, and we can also see the waveform what is the waveform. So, this type of waveform will appear if we want to measure the DC signal. If there is a DC signal, this type of waveform will appear on the screen. So, we can measure the amplitude of this signal by seeing how many division it covers and what is the position of this volt per division. So, this is the DC measurement. Then for the measurement of AC signal, again if we want to if we do not want to see the behavior of the signal, we do not want to analyze the signal, we just want to measure the peak to peak value or the amplitude of the signal. Then again we turn off the time based generator. So, when time based generator is turned off means there is no movement in x direction. So, the signal will appear as a line here, and then this we can vary by x position switch, we can vary the position of this signal, and then this waveform, it is not a waveform, it is a line. So, we can put this line in the middle position of the screen, and so we can calculate the amplitude of the signal. So, signal is applied between y input, and so this type of pattern appears at the screen when we do not want to see the behavior of the signal. Then suppose we want to see the pattern of the signal, that is we want to see the waveform of the signal. So, what we will see, what we will do, we will just put the this triggering pulse, triggering switch at internal triggering position. So, it will internally trigger the signal that is applied at the Y channel. So, input is applied at the Y channel, and at X channel there is a time based generator signal is fed, and that time based generator signal is synchronized with this input signal. If it is not synchronized, then some portion of the waveform may disappear. So, the time based generator signal is basically in sawtooth shape, this type. So, it means ki when this input signal appears at the Y plate, so that the leading edge of that input signal basically synchronize the time based generator circuit, and time based generator circuit starts to produce a sawtooth waveform. This is known as sawtooth waveform because its shape is like a tooth of a saw. So, this is so because of this here, when this input is at this position, so what will happen, the electron beam starts from this position, and when it reaches at this position, then means electron beam will move from left to right position. So, it will cover here, then this is known as trace period because it traces the electron beam on the screen. This is known as retrace period. So, when the sawtooth wave reaches at the maximum position, means electron beam will move from left most position to right most position, then it has to go back in the this left position to trace the next signal. So, what will happen when it reaches at the rightmost position, then there is a blanking pulse applied and the signal will move, the electron beam will move from right to left position, but at that time there is no display of the signal. If there is any display of the signal, then what will happen ki this will be superimposed on the previous signal and we will not see any, the signal is superimposed and we will not able to see the actual signal. So, this is known as retrace period. So, trace period is very wide and retrace period is very short, and during the retrace period the cathode is applied with a very high negative potential, so that no signal will appear. So, suppose this is the screen of the CRO. Generally this division is in multimeter and each division have 5 subdivisions. So, suppose as shown here that this amplitude, this peak to peak voltage covers the 4.3 centimeter, and then it is multiplied by the knob is at the position of 5 volt per division. So, per division means per centimeter. So, the total signal peak to peak will be 21.5. Okay. We can also find out the root mean square value by dividing the peak to peak voltage by root 2. So, peak to peak voltage of this signal is 21.5 volt. So, amplitude we can find by dividing this by 2. So, this is the amplitude of the signal. Now, we have to find out the frequency of the signal. So, for finding out the frequency of the signal, first we have to find out the time period of the signal. So, this is the time period of the signal, distance in centimeter in x direction. So, distance is 5 centimeter and the knob is at 2 millisecond per centimeter. So, this is 10 millisecond and this 10 millisecond when it is 1 by f, we want to calculate the frequency, then 1 by time period is the frequency. So, this signal has 100 hertz of frequency. Similarly, suppose this type of signal is displayed. So, we can calculate the value of the amplitude and the frequency of the signal. Similarly, CRO is acting as a voltmeter also, it also displays the waveform. So, a waveform display when the frequency of the input input time based generator is equivalent to the frequency of the input signal, then it will show the single waveform on the screen. And if suppose the input signal is twice the signal of the time base frequency. So, when the frequency of the input signal is twice the frequency of the time based generator frequency, then 2 cycles of the waveform will appear on the screen. So, like this way, if you see the 3 cycles of the waveform, it means the time based generator is 1/3 of the unknown frequency signal. Then we can also measure the, if suppose we want to measure very short duration pulse, then we can also measure the short duration pulse by using CRO. So, this is the way that suppose a short duration pulse we can produce by clapping our hands, or we can say some words on the microphone and then this type of signal is appears on the screen, and so we can measure the distance between 2 peaks and other things, that is also in one application of the CRO. So, now we want to measure the phase difference between the signal. So, there are 2 methods using for by which we can measure the phase difference. The first is the dual beam trace comparison with the calibrated time based generator, and second is the Lysagius pattern. So, first is suppose 2 waveforms are simultaneously applied at the input of a CRO in 2 separate channels, and suppose there is a distance d between the 2 waveform. Suppose d is the total time period of the waveform, small d is the distance in terms of the division or in terms of the time. So, this is the phase difference, this is small d is the basically the time difference or the phase difference between 2 signals. So, we can calculate, if we can manage in our CRO that 2 waveforms are displaying at this type, then we can calculate this by the scaling factor x is equal to 360 degree, because one cycle complete takes 360 degree. So, 360 by d. So, this the phase angle theta between the 2 waveforms are s into d, that is small d divided by capital D into 360 degree. So, if we put 2 waveform together, then we can calculate the phase difference between 2 waveforms by this formula, theta is equal to, that is the phase difference between the 2 frequency 2 signals are small d by d, where small d is this and capital D is this, into 360 degree. So, this is one method. The second method is Lysagius pattern. So, in Lysagius pattern, what we will do, we will apply one signal at one channel, another signal at another channel, and we will press the X Y button of the CRO. So, when we will press X Y button of the CRO, so different shapes will be appearing on the screen. So, these type of oval shapes appears on the screen, a circle will appear. If circle is appearing on the screen, it means ki there is phase difference is 0. Suppose this type of oval shape appears. So, here we want to measure the phase difference between the signal, 2 signals. So, if this type of ellipse is appeared on the screen, then if ellipse is between 0 to 90 degree, Okay. If it is between 0 to 90 degree with positive x axis, we will see from this position. So, there. So, if it is from here to this, so if it is between 0 to 90 degree, then we will apply this formula phi is equal to sin inverse x 1 by x 2, where x 1 is this position and x 2 is this position, means from there where it intersect x axis and the second intersection, that is x 1 by x 2. If the signal is from 90 degree to 180, like this way, the signal is from 90 to 180 degree, then we will apply this formula phi is equal to 180 minus sin inverse x 1 by x 2. So, by these two formula we can calculate the phase difference between two signals. So, these are the different patterns that appeared when we apply two signals, and when we press x y knob, or we can say that when we put x y knob at the x y position. So, here we can see that this ellipse, the angle difference, the phase difference between two waveforms are theta is equal to sin inverse, since it appears between 0 to 90 degree. So, theta is equal to sin inverse 4 by 8. So, it is sin inverse half and its value is 300. So, it may be 300 or the difference may be 360 minus 30 degree, that is 330 degree. Similarly, if this type of shape appears, ellipse appear, it is from 90 to 180 degree, then again here it is between this is 4 division and here it is 6 division. So, it is 180 because it appears between 90 to 80 degree. So, it is 180 minus sin inverse 4 by 6. So, it is 138 degree or 360 minus this one. So, similarly, there are different shapes available here, and by seeing these type of shapes we can find out the difference between the signals. So, similarly, we can measure frequency of the waveform. So, frequency we can measure by calculating the time period of the waveform by using the formula by calculating the time period of the signal, then f is equal to 1 by t. By this formula we can measure the frequency. The second method of the frequency measurement is again the Lissajous pattern. So, in Lissajous pattern what we will do, we will apply the unknown signal at the y plate and we will apply the known signal at the x plate. Means we have a standard source, by that standard source we are applying a signal that is at the horizontal plate. So, there are different type of wave shapes appeared, they are also ellipse. So, 1, 2, 3 that we can see here, if the frequency that is at x plate is half of the frequency which is applied at the y plate, means the unknown signal is twice of the frequency of the known signal, then 2 ellipse appears on the screen. So, this is the formula for calculating the frequency. The ratio of two frequencies, that is f y, that is the unknown frequency, and f x, that is the known frequency. So, f y is equal to number of line to tangent touching upon bottom or top and the number of tangent touching either side. So, means if suppose this is, so number of tangent touching at top is 1 and number of tangent touching at side is 1. So, it means the frequency of unknown frequency is equivalent to the known standard frequency. But here we can see the touching is 2, the tangent touching is 2 and here the tangent touching is 1. It means the unknown frequency is twice of the known frequency. Similarly, we can see other, here we can see it is 3 tangent touching and here it is 2. So, it means the unknown frequency f y is 3 by 2 of the known frequency. So, in this way we can measure the frequency of the signal, unknown signal, by comparing the frequency of the known signal. So, these are the different component testing patterns. So, suppose we want to measure, we want to see whether a component is working or not working properly if we are not having a particular tester for that component. So, these are the different standard pattern given by the CRO. If you purchase any CRO, then that CRO will give you a prescribed book, and in that manual, CRO manual, you will get this type of pattern. So, we can compare the pattern. If the pattern is okay, suppose that first pattern is, if any circuit or any resistance we want to measure, or the transistor we want to see whether it is short circuited or not. So, if one line appears, it means it is short circuited. Similarly, we can see there, if we want to check the base and collector junction of the transistor, and if this type of pattern appears, it means our transistor is working. Similarly, the junction EC, then FET we can see. Similarly, here are different patterns by diode, Zener diode, if below 7 volt, then this type of pattern will appear, it means our diode is okay, Zener diode is okay. If not appear, it means there is some problem in the Zener diode. Similarly, the silicon diode has this type of pattern, germanium junction diode has such type of pattern. So, we can also measure the component. So, by CRO we can see the waveform of the any signal, we can measure the frequency, time period and other things. We can also measure the component of the any component, we can see whether it is working or not by the CRO. Then what are the precaution required? The first thing is, every CRO, at the front panel of the CRO, the maximum frequency that can be measured by the CRO is given. So, the bandwidth of our signal should not increase with the bandwidth of the signal. So, means the signal which we are going to measure, the amplitude, the frequency of that signal should be less than the frequency of the CRO. So, first thing is bandwidth limitation is there. The second thing is that the probe we are using. If suppose our CRO has a 30 megahertz bandwidth, but the probe we are using is not having that much bandwidth. So, again we will not correctly measure our signal. So, we have to make sure that the probe that we are using is also having the same bandwidth. Then triggering. Triggering is also, the waveform of the triggering should be very whatever we require, the triggering should be correct. Then ground clip should be grounded, properly grounded, and it is pure, it should not produce inductive or capacitive component. Then bandwidth as given here, the 3 times higher than the highest for the analog signal and at least 5 times higher than the digital signal. So, this is all from my side.